So, welcome back. Transformations of cubics. You've given it to me now. Transformations of cubics. There's not a lot that's new here, but I am going to go through some stuff because I want you to have a chance to revise some of those skills where it comes to transformations of other functions. And I'm actually going to try and use this as a bit of a summary of some of the skills that will be your baseline skills for these types of questions in the exam. So I say if you're, particularly for those of you having trouble with dilations, there are some baseline skills that can get you through most questions, even if you don't quite understand the dilations or you can't work out the dilations. So here we go. First we have this this disgusting thing here that no one really likes. That's our standard transformational form of any function. We have our D is a constant added on the outside, a constant that is added, subtracted on the inside. B is the inside multiplier, A is the outside multiplier, and it does those four things that we learnt about. In the specific case of cubics, as with some of our other functions, A and B both don't need to be there. So there's our standard transformational form of a cubic. A and B can be combined together because we can expand the B value out. So it ends up being AB cubed, and we just write that down as one standard dilation. So we don't really have a horizontal dilation. And if you visualize a cubic, the one that's in this form, which I'll show you in a second, a horizontal dilation is actually kind of like a vertical stretch. So horizontal compression is the same as a vertical stretch. So we don't need B. That's the good news. H and K work very similarly to the H and K in quadratics and square root functions. So they provide the location of a central point. So H and K should be fairly easy to determine, and it's just A we have to deal with, that dilation. So that's where we're at. This is quite similar to quadratics and to square root functions, so be prepared for that. So there's my summary of what they are, and even though I was writing this down away from class, I still got lazy and wrote hori instead of horizontal, and Bert, so sorry about that. So let's talk about example 4. First of all, this purple thing, that is our standard cubic. A cubic in transformational form does not represent every possible cubic. Some of the cubics you saw last lesson look like this. They are not represented in this transformational form. So just keep that in mind, okay? This is a different type of cubic, and whilst we could set that up using transformations, that can be done, it's substantially more complex. So we'll deal with those in the next couple of exercises. In this case, you'll have a cubic. If it's in this form, up there, it will not have two turning points. It will just have that single point where it sort of flattens out. Maybe completely flattens out, maybe doesn't flatten out at all. So what happens is we go up here, we get to there, etc. This point is the center, and it's represented by H and K. And that point, here's a name for you. That point is called the point of inflection. So the point of inflection is where if you're mapping out the cubic, and you won't be able to see this on YouTube, but I'm going to do it with my hands. If you're mapping out the cubic, as I go up the cubic, my hand is curling, so I'm sort of coming around and going to head back down. I'm doing that. The point of inflection is the exact point where my hand starts to curve back the other way. So the change in the gradient starts to revert back to the other way. The gradient stops decreasing and starts to increase. And when we start calculus, we'll deal a lot more with that. For now, you don't have to worry too much about that, but that point of inflection is where the flattening out stops and it starts to increase again. And so if you're mapping it with your hand, you've got curving down, curving up. That's where that changes. And that is our center. So we get our H and K from that. So I'm going to do the first one, and I'll talk about the second one, which is a little bit different. So the first one has, I'll do it entirely in purple. No, I've already used purple. I'll do it entirely in light blue. Hopefully it's dark enough. Has an H value of 1 and a K value of 3. So my H value is 1, takes me to here, and my K value is 3, which takes me to there. So this is the coordinate 1, 3. There. And then I also have a dilation, so my A value equals 2. So it's been stretched. Now, here's your saving grace. I'm going to do this in a different way. If you can't deal with the stretch factor, and the cubic's not too bad because we've got that 1, 1, so it basically means we go along 1, up 1. So from this point we go along 1, but we actually go up 2 because the dilation's 2. So you might be able to deal with that. But if you can't, if you're not sure, we will have to identify the critical points irrespective of how you draw your graph. Can anybody tell me what the critical points are for a cubic function? There are typically 3 of them. Turning point is definitely critical points, but not in this case because this is that particular cubic with no turning points. But yes, definitely in the next exercise that's true. I'm looking for 3 for this one. Yep. X-intercept and Y-intercept are 2 of them. And what's the other one? Well, they're the H and K point. What's that called? Point of inflection. Good. So your target, whenever you're drawing a function, should be to identify all the critical points, which will be x-intercepts, y-intercepts, point of inflection, and turning points in the functions that have turning points. For hyperbolic functions, it will be identifying the asymptotes. They're critical points as well. And that's pretty much it. So you're looking for those. A cubic function starts low, finishes high, starts high, finishes low, one of those 2. It will always have an x and a y-intercept. They might be the same point, but they will exist. If it's on the origin, it'll be the same point, okay? So in this case, I've already identified the point of inflection. How do I go about identifying the x and the y-intercept for any function? 0. They're both 0? X and y-intercept are 0. Do you want to expand on what you just said?
You said x and y is 0.
Excellent. Okay, so what we do is for the x-intercept, we let y equal 0, and then we solve for our function. So in this case, we get 2x minus 1 cubed plus 3 is equal to 0, which gives us 2x minus 1 equals negative 3, which gives us x minus 1, so that should be cubed. Cubed equals negative 3 over 2. X minus 1 equals the cube root of negative 3 over 2. Now you might be looking at that and going, oh, but you can't take the square root of a negative. You can take the cube root of a negative. So be aware of that. That might happen, and that can happen. And therefore x is equal to 1 plus, that shouldn't be a 2, sorry, that should be a 3. 1 plus the cube root of negative 3 over 2. And at this point you can get your calculator and you can determine that cube root. It's going to be not nice, but we'll do it anyway. 1 plus, I'm going to do it on my calculator the easy way. I'm going to put negative 3 divided by 2 in brackets and then raise that to the power of 1/3. Because 1/3 is the same cube root. I find that a bit easier on here. And I get, and check that you get the same, 0.145, rounded to 3 decimal places. And the y-intercept is usually easier. It's when x equals 0. And so, it is negative, yes, thank you. Negative 0.145. The y-intercept is a little bit easier. We get y is equal to 2 times 0 minus 1 cubed plus 3, which is negative 2 plus 3, which is negative 1. And so that means my y-intercept for this function is at negative 1, 0, negative 1, and my x-intercept is at negative 0.145. Is it negative? I don't want it to be negative. Cube root of that will be negative. Oh, sorry. No, I know the problem is. Negative 2 plus 3 is positive 1. So this is not my y-intercept. Let's change that and do it properly this time. My y-intercept is at 1. So I get the term 0, 1 is there. And I get this point here, which is negative 0.145, 0. And now I can draw my cubic function. It turns here, so it goes up there, although it's quite steep, so I should represent it as being quite steep. And it goes down there. And I've got my 3 critical points marked, and my function is in the right spot. That's actually all we ask in the exam. It doesn't have to be perfect. You don't have to align everything in the right grid positions. If you have the critical points marked and labelled and your function looks appropriate and about right, then you'll get full marks. Okay? If you are not as good as somebody else at sketching, that shouldn't detriment your ability to get full marks here. And what can you do to make sure you get this right before you even start the question? Just sketch it in your graphic calculator. Have a look at it. You'll know what it looks like. The second one, which I'll do fully in pink. So B, I'm going to bring it down here because I'm going to run out of space. B is 2y plus 3x cubed equals 8. 2y plus 3x cubed equals 8. That gives me 2y is equal to negative 3x cubed plus 8, and y is equal to negative 3 over 2 x cubed plus 4. Can anybody tell me where the point of inflection lives? Okay, so for those people that are just talking at the moment, you might want to pay attention to this bit. In this case, note that this function has an h value of 0 and a k value of 4. So the whole function has been translated up by 4. That's what this 4 does. But there is no h value. So it's not being translated left to right. The point of inflection is at 0, 4. You make sure you're looking, you understand the h value has to be in there with the x. If it's just x, then it's like x minus 0, and nothing's happened. The 4 is the vertical translation. There's our point of inflection. And now I might go ahead and try and find my y-intercept and my x-intercept, Felicia. The standard form. That one there. So you've got your h, your k, and your a. That's what you're looking for. In this case, I can see that my A is equal to negative 3 over 2, and you might be able to deal with that yourselves. But in this case, because A is not a nice, easy, positive or negative integer, I would probably actually just find my x and y-intercepts and move on. Now, the y-intercept's easy. Can anybody tell me what the y-intercept is? The y-intercept's just 4. So that's I've already done number 1. So point number 2, the y-intercept, x equals 0, y equals negative 3 over 2, 0 cubed plus 4, which equals 4. Point 3, the x-intercept is when y equals 0, and I get 0 equals negative 3 over 2, x cubed plus 4. And now I can go about rearranging this. I get negative 4 equals negative 3 over 2 x cubed. And therefore, 8 over 3, I've just done that quickly, but you can do that in your calculator, equals 8 x cubed, and x is equal to, the cube root of 8 is 2, over the cube root of 3. That's not nice. And again, I just determine this, 2 divided by 3 to the power of 1/3 is equal to 1.387. When I plot these 3 points, the graph should be a cubic with no turning points. The point of inflection is on the y-axis, but the x-intercept should allow the graph to be a flipped graph because my a value is negative, so it's flipped over. So expect to see a flipped graph now, and I'm going to go up here and plot those points. The first point was here at 0, 4. That's also the y-intercept. The x-intercept is here at 387. I was thinking 4. I don't know why. 387, 0, and my graph looks like this. That's a cubic, but it's been flipped over because it's a negative a value. Any questions on that? Worst case scenario, you find your point of inflection and then you find your x and y-intercept. The same thing holds for hyperbolic functions, square root functions, maybe not so much circle functions. X and y-intercepts are quite tricky for those, but hyperbolic and circle and square root functions, find your x and your y-intercept, and you will be in a good place. You can get most, if not all, of the marks just for doing that and plotting the function. Okie dokie. Is that a question, or is that laughing at me saying okie dokie? Chris? Yes, I can, but I've almost finished, so I'll come over and I've done that. Okay, here's function C. What I'm going to do is I'm actually going to pause my recording, give you 2 minutes to have a play with this, and then I'll put it back on and finish this question. So you've got 2 minutes.
Hi, recording.
Sorry.
Hi, recording.
Thanks, Sophie. No, it doesn't count down from 3 for this bit. Okay, did anybody, sorry, thanks. Anybody got any first steps on how we could do this question? Sorry, I couldn't hear Alicia. Sorry, say that again. Find the point of inflection. Can you tell me what the point of inflection is? -2, -2. Excellent start. And what are we going to trade that for? Alicia, you're on a roll. You may as well finish the point of inflection bit off. How are we going to put that into our standard form? H and K. This is my H and K. So I put that, just, can we not be shouting out? I can't hear people then. We are, sorry? Oh, sorry, it is a cube. So y equals a x minus -2 cubed minus 2. Y equals a x plus 2 cubed minus 2. Some of you might be going, yeah, we know that's a positive. Why do we even bother with this step? But I tell you what, little mistakes like that continue to ruin people's exams, and people continue to say, I'll go up and say, do some work in your book, actually show your working, show me what you're going to do in your exam, and they go, no, it's fine, I'll do that in the exam, and then they get it wrong in the exam, and they make little mistakes with negatives. So please make sure you're showing that working. And how do we find the A value? Hands up. Substituting point, which point do you want to use? 0, 2, what we said? 0, 2. So, ladies and gentlemen who didn't listen there, substitute in another point. 0, 2 is a great point. It's clearly marked. I've done that deliberately. That might not be the case in your exam. I did that deliberately here because you might not be able to see it up the back. Clearly marked here. Do not use any points you've already used. We've already used that point. Do not substitute that in to try and find A. It won't work out. You'll end up with 0 equals 0. Okay? If you use your x-intercepts to build a quadratic function, don't then use them to try and find your dilation. You have to find a different point. We haven't used the y-intercept yet though, so I'm going to substitute in when x equals 0, y equals 2, I get 2 equals a times 0 plus 2 cubed minus 2. I add 2 to both sides to give me 4 equals a 2 cubed, and then I divide by 2 cubed to give me a half. 2 cubed is 8, by the way, equals a, and therefore y is equal to a half x plus 2 cubed minus 2. And there's our function. So getting a cubic function, and this holds for hyperbolic functions and square root functions as well. Substitute in to find your translations are easy. H and K in this case is your translations. H and K in the square root function form are your translations, and the asymptotes in your hyperbolic form are your translations. Find those, and then in all those forms you only need to find one other point to find your A value. Bam, you're done. And there's my function. Exercise 8E, I'm going to give you 10 minutes to try and do 2 of those if you can, maybe 3. Thanks.
You're welcome.
Sophie?
See you later.